Have you ever just stopped and wondered how a large language model can write a poem, or spit out code, or just talk to you in a way that feels so human? Well, it's not magic. It's an incredible piece of engineering called the transformer, and in this explainer, we're going to pop the hood and see exactly how it works. You know, the biggest challenge for AI for years was just getting context. How can a machine know that the word bank means one thing when you say he sat on the riverbank and something completely different in he went to the bank? That ambiguity was a massive hurdle. And the transformer? Well, that was the breakthrough built to solve that very problem.
So first things first, we've got to translate. Computers don't speak English, right? They speak math. So before anything else can happen, we have to turn our words into numbers. This whole process is called embedding. Basically, every single word or token gets turned into a long list of numbers, what we call a vector. But here's the cool part. These are not random numbers. The model actually learns to arrange these vectors in this giant multidimensional space where words with similar meanings get placed closer together. And this is where it gets really mind-blowing. This vector space actually captures relationships. I mean, check out this classic example. If you take the vector for king, subtract the vector for man, and then add the vector for woman, you land almost exactly on the vector for queen. That is pure mathematics capturing these really abstract human ideas like gender and royalty. It's incredible. Okay, so all our words are now vectors. Great. But a sentence isn't just a jumble of words, right? The relationships between them are what create meaning. So how does the model figure all that out? Well, that is the job of the transformer's secret sauce, the attention mechanism. Before transformers came along, older models like RNNs had to read a sentence one word at a time. And this gave them a terrible memory. I mean, by the time they got to the end of a long paragraph, they'd literally forgotten what was said at the beginning. Transformers changed the whole game because they look at the entire sentence all at once in parallel. This whole idea came from a 2017 paper with a perfectly blunt title. The researchers knew they were onto something huge. They figured out that this attention thing wasn't just part of the solution, it was everything.
So how does this self-attention even work? Well, for every single word in a sentence, it basically asks, okay, which other words here are most important for understanding me? It does this by creating 3 special signals for each word. A query, which is like asking, what am I looking for? A key, which is like saying, here's what I'm about, and a value, which is, here's the actual stuff I mean. By comparing every word's query to every other word's key, the model calculates these relevant scores. Then it creates a brand new, context-rich version of each word by blending the values of all the others, based on who screamed the loudest.
But, and this is a huge but, there's a catch. To figure out all those scores, every single word has to look at every other single word. This means the amount of computation just explodes. A 10-word sentence, that's about 100 calculations, but a 100-word sentence, that's 10,000 calculations. This quadratic growth is exactly why these models can sometimes choke on really long documents.
Okay, so attention is how the model understands context within the stuff you give it. But what about all the general knowledge it has? You know, where does it store a simple fact like Paris is the capital of France? Well, that's the next big piece of the puzzle.
Yeah, that's a fantastic question. That knowledge, the fact that Michael Jordan plays basketball, it's not figured out by attention. It's actually stored in a totally different part of the model that acts like its long-term memory.
That information lives inside something called the multi-layer perceptron, or MLP. Think of it like this. After the attention layer lets all the words talk to each other to figure out context, each word's vector then goes one by one into the MLP. It's in this private little processing step that the model dips into its huge library of stored facts to make that word's meaning even richer. You can almost imagine it as a massive collection of if-then rules that it learned from all its training data. The MLP scans a vector for a very specific pattern, like the combination of Michael and Jordan. If it finds a match, a little switch flips on, and it adds the relevant fact it has stored, in this case, basketball, right into that vector before passing it along. And here's the kicker. While attention gets all the fame and glory, these MLP layers are the real heavyweights of the model. They make up roughly 2/3 of the model's entire size. So for something like GPT-3, that's over 100 billion parameters whose main job is just storing facts. All right, now for a really fascinating and kind of tricky part. We often think that AI bias comes from being trained on biased data. But what if the machine itself has its own built-in tendencies?
Turns out, the transformer architecture has a few ghosts of its own. The way a transformer is built, the very structure of it, isn't neutral. It actually has its own weird preferences and blind spots that can totally shape what it says, completely separate from the data it was trained on. Take this, for example. Research has shown that transformers have a really strong bias for information at the beginning and the end of a long prompt. They pay super close attention to what you say first and last, but details that are buried deep in the middle, yeah, those can often get ignored or just lost. And that's not from the data, that's just a weird quirk of the architecture itself. Here's an even sneakier example. These heat maps are showing where the model is paying attention. On the left, an instruction was given directly by the user, but on the right, that same instruction was hidden in a system prompt that the user can't even see. Look at how differently the model behaves. Its output can be totally swayed by these invisible instructions, introducing biases that a user would never even know are there. Okay, we've gone from words to vectors, we've mixed them all up for context, and we've sprinkled in some facts. Now for the grand finale. How does the model turn all of that complicated math back into a single, clean word? So after a vector makes its journey through all the layers of the transformer, it's used to generate a raw score for every single word the model knows, tens of thousands of them. But these scores are kind of messy. That's where a function called softmax comes in. It does this really elegant thing where it takes that giant list of scores and cleans it up into perfect probabilities, where every word gets a value between 0 and 1, and they all add up to exactly 1. And this, right here, is basically the model's final decision laid out for us. It is assigned a probability to every word in its vocabulary, and the word with the highest probability becomes its best guess for what it should say next. And this is the part we can actually control. When you see a setting like temperature, you're really just controlling randomness. A low temperature makes the model play it safe and pick the most likely words, making it more predictable. But crank that temperature up, and you're encouraging it to take risks on less common words, making it more, well, creative. So we've seen the whole assembly line: embeddings, attention scores, MLPs, probabilities. It's this breathtakingly complex system for matching patterns and making predictions, which of course leads us to the final, really big question. Are we actually building something that understands the way we do? Or are we just building an incredibly convincing mimic? That's definitely something to think about.